Hello everybody. So I got a question yesterday, I guess, about this particular problem in MyMathLab, and at least at the time I'm making this video, this is question 8 from assignment 3.2, and it's a big question. It's very involved, but I had my reasons for wanting to include it in the assignment. Um, but anyway, let's just go through it one part at a time because like I said, it's involved. Some of it is very tedious, but I've worked this problem myself start to finish just like you would. All right. So it says here that we're given a population, and that population, as far as the data goes, is the word counts of 5 essays. Okay, 510 words, 621 words, so on and so forth. Okay, and then there are several questions that ensue after that. The first two questions is, what is the mean of the population and what is the standard deviation of the population? Okay, so the population is the word counts of these 5 essays. Well, this is the kind of thing that we've used StatCrunch in the past for. So what I'm going to do is I'm going to open this in StatCrunch. And I'm going to go to Stats, Calculator, or sorry, Summary Stats, Columns, select the column VAR1 because that's where my data is, and then I want to calculate the mean and the standard deviation, right? Because that's what the question is asking us, at least the first two parts. So I do compute and I get a mean of 574.2, all right? And then I get a standard deviation of 44.5499, but that's not the right answer, okay? Now, this may very well be something that you've forgotten, okay? Something's not right between these numbers, the standard deviation that StatCrunch gives me and whatever the correct answer is for the standard deviation of the population. So, real quick, there are a population and a sample are different. That's been a theme throughout most of our class, okay? In statistics, what we do is we have a population of some kind, and we take the sample from the population in order to study it or know something about it. They're two different things. Populations and samples are different. Sometimes the math is different for them too. The way we do calculations is different sometimes, okay? So, here's my warning to you. StatCrunch calculates the sample standard deviation by default. So, this number is a sample standard deviation, not a population standard deviation. They are different. Samples, the standard deviation of a sample is different than the standard deviation of a population, all right? So, here's what I would need to do in order to fix that. I'll give you a formula for conversion. If you take the sample standard deviation, which StatCrunch gives us by default, and you multiply it by root n minus 1 over n, where n is the size of the population, okay? Then you'll get the population standard deviation. So in my case, the population was these 5 numbers. That would be, n equals 5, n minus 1 is 4, n is 5, so I get 4/5, root 4/5 times, you see that 44.549972? That's this number right here, okay? So yes, just like this formula says, I'll take root 4/5 times the sample standard deviation. I'll get 39.85. That's the population standard deviation, okay? So I mean, that's kind of maybe an annoying thing, but that's the way it is. So now that's true for standard deviations. They're different between the sample and the population. As far as the mean goes, the mean of a population is the same, can be calculated the same way as the mean of the sample. That's why I didn't have to adjust this number, okay? So that's part 1, all right? So let's go back here. The next part, it regards the sampling distribution, okay? And I've already made a video on what that is without regards to this particular problem. But let me kind of get you thinking about it as much as I can real quick. So remember I said that we have a population of some kind, okay? And the population has a mean and a standard deviation. We use the Greek letter mu for the mean and the Greek letter sigma for the standard deviation of the population. Okay, so that the population is out there and we want to study it somehow. Okay, and what we do is we take samples. Those samples will be of a certain size. So let's say we take samples of size n. And let's say that in addition to that, we calculate the mean of the samples. Okay, and by, the mean is like the average. So okay, and we'll call that symbol for that is x bar. So mu is the mean of the population, x bar is the mean of a sample. All right, so we take samples of a certain size, let's say that it's size n, and I find the mean of each sample. What is the distribution of that? What is that number like? That's our question. So the sample mean, you take these samples, you find the mean or average of each sample. That's its own number, and like now we're trying to study what's that number like. Okay, so the answer is that the sample mean has its own distribution with a mean the same as the population mean and a standard deviation being sigma, the population standard deviation, over root of n, the sample size. So when I say that the sample mean has its own distribution, meaning that like it's spread out and it's like, it has its own average or middle and it's spread out a certain amount. That's what the mean and the standard deviation tell me. Now that's like, there are a lot of layers to that. I understand, the population versus the sample versus you take the mean of the sample and then the sample mean has its own distribution, its own average and its own spread. That's what the mean and the standard deviation tell me. I understand that there's a lot of layers to that, but that's the way that it goes. Okay, now so here in this question it says identify all samples of size 2 with the correct accompanying means below. Now this part is tedious, like I can admit that I worked this question myself and I didn't take any shortcuts, but I included it because I just wanted a way for you to think about this flow chart, that we have the population, and when I say we take samples of a certain size and we calculate the mean of the samples, and then the mean has its own nature, I just wanted a question where like you are putting your hands on that being samples of size 2 in this case with the mean of each sample below. So here's what I did. Like I didn't take any shortcuts. I worked this the same way that I'd have you do it, and like I admit it's a little bit tedious, but when you do math and technical things, sometimes it gets a little bit tedious. That's the way that it is. So here's my population, and I wrote down every sample of size 2, and I tried to do it in an orderly way. So I took 5, 10, 6, 21. I took 5, 10, 551. I took 5, 10, 606. I took 5, 10, 583. You see the pattern? Then I took 621, 551. 621, 606. 621, 583. So I tried to go through it in an orderly way so I would not lose track of anything. Okay? So that's one thing. Now, also you see that for the sample of size 2, 5, 10, and 621, here's the sample mean, 565.5. How did I get that? How do you find the mean or average of two numbers? You add them together and you divide by 2. And if you do that, you'll get 565.5. And I did that, like I said, I was like, no shortcuts. I just use my handheld calculator. Here for this one, 510, 551, how did I get the sample mean? I added these numbers together, divided by 2. All right, so that's what these X bars are. Here's the mean of every sample. Now, when we talk about all samples of size 2, it's like, here's my population, pick 2 numbers, okay? Now, it may seem strange, but it's also considered a possible sample to get not only 5, 10, and 621, but 621 and 510. Not only 510 and 551, but 551 and 510. Okay, so notice that I got 1 through 10 here when I just selected these and kind of in an orderly way. And then 11 through 20 are just what you'd get if you had picked them in the opposite order. I didn't write the sample mean for 11 through 20 because it would be the same. You know, the sample mean for 510 and 621 can't be any different than 621 and 510. Okay, so I got those. So now I'm up to 20 possibilities. And then one more thing, like here, I'll just pick two numbers blindly, right? And so far, these are the possibilities I give you, all right? But I could pick 510 twice. That would also be considered a possible sample of size 2. I could pick 621 twice. I could pick 551 twice. I could pick 6. You get the idea? And I'll calculate the sample means of those. So here's all possible samples of size 2. Okay? That's what considered all possibilities. Now, from here, I would have to pick out all those possible. What I did when I worked this is I wrote them down like this, calculated the sample mean, and then picked them out one at a time. All right? So I didn't take any shortcuts. I didn't have some magic easy way to do this that I'm not offering to you. I just did it the hard way. All right? It didn't take that long. It looks worse than I think it actually is. Okay, so that's how I did too. So this, you know, when I talk about, you know, we're going to have population, we take samples of size 2. We calculate the mean of each of those samples. That's the number I'm curious about. This X bar, this sample mean. Now I want to say, well, what's that number like? The mean of the sampling distribution and the standard deviation of the sampling distribution are next. So that those numbers basically tell me where is the middle of X bar, like all these X bars, if you like plotted them out on a graph, where would roughly the middle be? And the standard deviation is the spread. If you had a graph and you plotted all these X bars, how spread out would they be? Remember, the standard deviation measures the spread of data, or the mean roughly measures the middle. Now, okay, so for that, here's how we would go. So X bar is the sample mean. It has its own distribution and its own standard deviation. For the sample mean, its own mean is the same as the population mean, which we already calculated to be 574.2. Okay, so the mean of the X bar distribution, 574.2. The standard deviation, that's a little bit different. Standard deviation of the sample means distribution is the population standard deviation, which we calculated up here with a little help from StatCrunch to be 39.85. Okay, and over the root of the sample size. So we take 39.85, and we were taking samples of size 2, so we say 39.85 over root 2, get 28.18. Okay, so there are the mean and standard deviation of the sampling distribution. Or like I said, if we plotted out, if we had a graph and we plotted out 530.5, 578.5, imagine all these dots everywhere, wherever these numbers are. The mean is where roughly the middle is, and the standard deviation is a rough measure of the spread, okay? For X bar, for the sample mean of all samples of size 2. Okay, all right, so we did all that. We had to know what the appropriate formulas are for the sample means distribution. Okay, but I give you those. And last thing, it just says, well, what comparison would be accurate? And between the population and the sampling distribution, the means are equal, right? That's just part of it. But in this case, the standard deviation of the sampling distribution is smaller, okay? Which will be the case. All right, so that's how we tackle this one. A big question, mainly because of this part right here. But, you know, when I say that we're going to do this and we take samples of size whatever, and I want to know about the sample mean, I want to know about that number. Here they all are. This is what it's like. All these X bars. I'm talking about how to characterize that number in terms of a mean and standard deviation.